system of particles. So we are discussing about oblique collisions in the last lecture, and we had seen the basic idea that typically if we have a situation where a moving body moves, goes and collides with a stationary object, then typically we have four unknown quantities, because after impact, the final velocity's directions are unknown. So there are, effectively two unknown angles, and the magnitudes of the velocity are unknown. Or if you take the velocities as vector quantities, so it's a two-dimensional situation. So you have two unknown velocities, the final velocities, which means you have two unknown components per vector. So you have four unknown quantities in all. So if this is the initial velocity vector V0, let's say, with which a body A is moving, and it goes and collides with another object at rest like this, then we had seen that on impact, there is what we call the line of action or the line of impact, which is the line along which the collision impulse acts. So typically, if the body is colliding as spherical or disc shaped or something like that, then it's very easy to determine the line of impact. The line of impact will be the normal line, which is basically the center to center line, because the plane of impact will be this tangent plane. So for round shaped objects, it is very simple matter that the center to center line then becomes the line of impact. So the collision impulses act along this line of impact. And from there, it is very easy to understand that the final velocity of the second one will be along this line of impact, whereas the final velocity of the first one will be along some random direction, which is determined by both the things, the initial velocity vector as well as the amount of impulse acting. So if this is the collision impulse, the mutual collision impulse, this is the impulse on B because of A. This is the impulse on A because of B. So this line of action is supposing at an angle of, so this was the direction of this one's initial velocity. So one of the important aspects becomes this angle. If this angle is known to us because of some geometry, then one equation automatically comes from there. So this is the impact impulses. Okay, and once this collision situation is over, then we can see that the first body will tend to go off with a final velocity, which will be at some kind of angle to this line of impact, or we can even treat it as some angle with respect to the initial velocity vector. Whereas the second one will go exactly along the line of impact, because the impulse acting on it will be equal to the final momentum, because it was at rest initially. So if this has a velocity Vb, this has a velocity Va, then with respect to that initial velocity V0's direction, if this is some beta and this is some alpha, so we can see that alpha, beta, magnitude of Va and magnitude of Vb, these are the unknown quantities. So we have conservation of linear momentum for the system. This will give us two equations, because we'll take components. Then some kind of geometrical consideration will give us one additional equation. It will give us alpha or beta or something like that. And then finally, we'll also have to use the value of coefficient of restitution. So that is the general method of solving the oblique collision of this type, a moving body going and colliding obliquely with another stationary body. So let us look at some examples. Now, when we write this conservation of linear momentum in two equations for components, how we take the components is up to us. We can take the axis with respect to the initial velocity vector v naught being the x-axis, or we can also take the line of impact, this line, as one of our axes. It all depends on what is more convenient for us. So sometimes it is more convenient to take the line of impact as our reference axis. So for conservation of momentum equation in component form, we may take line of impact as an axis, or we may take the direction of v naught, the initial velocity of this guy, the first one, as the reference. So alternately, the line of the initial velocity vector v naught as an axis. It's really a matter of choice. Okay, and it's a matter of convenience. So that is what we'll understand in the upcoming questions, how to do this. So just get familiar with this general idea first.
So noted.
Yeah. Okay, so let's see how this works out with a typical type of question. Okay, so let's say we have this situation. We have so we have this body A, which is a disk of radius 2 millimeters, and mass equal to, let us say, 3 kilograms, moving with a velocity of 15 centimeters per second, like this. Now it goes and impacts a second body, which is also a disk but of larger radius. So like this. So this is a stationary disk B, which has radius of 3 millimeters and mass of, let us say, 6 kilograms. Or let's make this mass of 7 kgs. Okay. And now the additional parameters given to us, which is this. I'll just explain the parameter. So the velocity vector of this one, it is, let's say, like this. This is the velocity vector. Okay. So that is our v naught. So now if we draw what we call the line of action of this velocity vector, this, okay. And if we compare this line with respect to the center of disk B, which is this one, then this is at a distance, this is at a perpendicular distance of D. So this is called something called the impact parameter. Okay, so also given that the impact parameter that D is 4 millimeters. So impact parameter is defined as the perpendicular distance of the vector V0 line of action with respect to the object B's center. So basically you can say it is the distance by which it misses the center. Okay, had that impact parameter being 0, if D is equal to 0, then it's a head-on impact. Okay, if D is greater than 0, but less than R1 plus R2, that constitutes an oblique impact. And obviously, if D is greater than R1 plus R2 itself, then there is no impact. It completely misses. And in the unlikely event that D is exactly equal to R1 plus R2, what happens is that it just about grazes. You can say it touches tangentially and moves off. So there may or may not be any impact that actually occurs in that case also. So that becomes a bit ambiguous. Okay, so this is the general idea about impact parameter. Okay, so this impact parameter is given to us as 4 millimeters, and the coefficient of restitution for this collision is given to us as 0.8 or 4 by 5. So we have to find the final velocities of A and B after impact. And we also have to find the collision impulse itself. Okay. So first of all, I would like you to work out that from this information that is given, a lot of geometrical information is given. There are 3 things given: impact parameter, B, and the 2 radii R1 and R2. See how that is going to help us over here. Right? How it's going to give us some extra information as far as the collision is concerned. Remember, in solving the collision, we have to basically solve 2 vectors. So that is basically 4 components, or 2 angles and 2 magnitudes. So see how this geometrical information given is going to help us with respect to that. Okay. Then we'll discuss about how to implement the coefficient of restitution also. Okay. And while implementing that, keep in mind that we have the option of taking the components of the vectors according to axis of our choice. So we can use the center to center line, that is a line of impact along which the impulse actually acts. We can take that as our x-axis. That might be convenient. Or on the other hand, we can also take the line of action of V0 as our x-axis. That might also be convenient. So as may be the case, whichever is more convenient, we will go with that option.
So we can find alpha.
Yes, very good. So that information is going to give us alpha. Okay. So now just make a proper diagram and try to figure out how much will be alpha.
53.
Sorry, how much it is?
53 degrees.
53 degrees. Very good. That's correct, Beta. Good. Okay. Now try to figure out how you can write the momentum conservation equation. Okay. My hint to you is use the center to center line. That is the line of impact. Try to use that as your x-axis when you're doing the resolution into components. It will be more useful because your final velocity of B is along that. So it will have only the x component B will have. Okay.
So we can't find beta anyways, right?
You'll have to find beta somehow. So again, the hint to you is you have one more information. No? Coefficient of restitution is given to you.
Yes, sir.
Okay. So see, four pieces of information you require. So conservation of momentums, 2 components equation, then 1 geometrical equation from which you got alpha, and beta will be one unknown, but you will use the fact that coefficient of restitution is 0.8. So approach velocity, or rather separation velocity, is 0.8 times approach velocity, or 4 by 5 times of approach velocity. So first of all, you have to figure out how much the approach velocity will be. It won't be V0, no? So that's where again alpha comes into play, right?
Yes, sir.
Okay, so let's look at how this is working out. So first of all, let me draw a somewhat magnified kind of diagram. Okay, so this is our contact, let's say. Okay, and I will look at this in just before impact situation. Okay, and I look at it again during impact when the impulse is acting. And then again, I'll look at just after impact. Look at it. So I'm looking at three diagrams which are a succession of events which are very close to each other. So the first one is when they are just about to come in contact. Okay, so as of now, no impulse is active or no force is acting, but they're just about going to come in contact. So that time, this V0 is like this. Okay. And as you can see, the line of action of V0 is going to be at that perpendicular distance D which we have written. So if just as they are coming in contact, this is the center to center line. So you can say that if this is the center of B and this is the center of A, then this distance CACB is R1 plus R2. Okay. And if I drop this perpendicular here, this is the impact parameter D. Okay, so as you have correctly worked out, okay, this angle alpha can be determined from this. Alpha is sine inverse of D upon R1 plus R2, which in this case is working out to be sine inverse of 4 by 5. So that is our well-known angle of 53 degrees. So that is one piece of information I'm getting directly. Okay. Another thing that you can see over here, that the approach velocity of A towards B is how much? It is the component of V0 towards B center. So it is V0 cos alpha. So it is 15 centimeters per second into 3 by 5. So 9 centimeters per second is our approach velocity. Okay. So now what I will do is I will take, first of all, I will show the collision impulses which are acting. Should be acting along this line. Just in terms of magnitude, they are equal. So I'll write them as J each. Okay. But more importantly, now what I will do is I will define this as my system of axis, which will make life very convenient. We'll see why. I take this as my y-axis, this as my x-axis. Okay. So what you will see in the second diagram, you will realize from that diagram is that for A, its x component of momentum will be conserved. So what is the momentum of the system initially? It is A's momentum only, which is ma into V0. So the momentum of the system right now, initial momentum, is equal to mass of A into V0, which will become ma into V0 cos alpha I cap plus sin alpha j cap. Okay. Now here, notice that the impulse acting on A because of B is along minus j cap. Therefore, A's x component of momentum is conserved. That's very important. Okay. So that's why we come to this, that in the picture finally after impact, Suppose because of this large amount of impulse, E's y component of momentum gets reversed in direction. Suppose this is what happens. So this is VA's y component, but A is still, sorry, x component, not y component. But A still has an x component, rather A still has a y component of momentum, which will remain conserved from before, because there's no impulse acting in that direction. The impulse is acting only along the negative I cap. Okay, so I have mixed this up here. Just make this correction. Yeah, so the impulse acting on E is along minus of I cap, the negative x-axis that I've chosen. Therefore, its y component of momentum is conserved. Okay. Hence, like, you're getting one component directly over here. This VAY should be equal to nothing but V naught sine alpha. Whereas B will, of course, go up with a velocity in this direction, which will be purely in this direction. So E's velocity after impact will actually be, you have to calculate it this way. You have to calculate it this way, and we can even work out the angle and all that later. Okay. So now you can see I have actually three unknowns: VAX, VAY, and VB. Now out of that, one I will get directly because there's momentum conservation for E along the y-axis. Okay. So that I'll get directly, and VAX and VB, those are the two unknowns remaining, for which I will have to use a combination of two concepts: momentum conservation and coefficient of restitution.
So the value of beta 10 not calculate. I cannot calculate it. 10 beta is equal to 108 by 169.
We can calculate with a tan beta. For that, we'll have to again use vector algebra. Like we know V naught as a vector quantity in this coordinate system, and we will know VA as a vector quantity in I cap J cap notation, and we can use dot product and all that to find the angle between them. That will give us beta. Getting my idea?
Yes, sir.
But let's start by finding out the components themselves. So now you can see that what is happening, that after impact, VA's velocity, A's velocity VA, I'm writing it as some minus x component and some positive y component. And this positive y component, by the way, will be how much? This will be V naught sine alpha because of this. Okay. Whereas B's velocity I'm writing as VB I cap. So the final momentum of the system now will be equal to mass of A into this velocity plus mass of B into this velocity. So when I compare the final momentum with the initial momentum, that will give me one additional equation from which I will get one relation between VAX and VB. And VAY I already know. So now I'm down to two unknown quantities, VAX and VB. And one equation which I've got from momentum conservation between them. The other equation I'll have to get from the coefficient of restitution. Okay. Masses were 3 and 7 kg. Okay. Masses of A and B were 3 and 7 kg. Let me write that down here also, so you can start working on the final step if you have written down up to here. So these are the masses, and the coefficient of restitution was 0.8. Okay. So this is the picture just before impact. This is during impact, as the impact is taking place. And this is just after.
So we'll not introduce a beta.
We'll find beta later, but in our equations we will not need it, because we've written in component form the equations.
Yes, sir.
Okay. Okay, so let's write this momentum conservation equation now. So we can just, actually this momentum conservation equation itself will show us why is y component of velocity remains v naught sine alpha. We just equate the initial momentum with the final momentum for the system. So we can see the initial momentum is mva into cos alpha a cap plus sine alpha j cap. Sorry, mv naught, by mistake. Right, so this is mv naught as a vector. Now this should be equal to MAVA as a vector plus MBVB. So MAVA as a vector is again like this. We have written it in component form, having a negative x component. Now I've assumed that it has a negative x component. It may well have a positive x component also, but it's lighter by quite a value, 3 kg compared to 7 kg. So I've assumed that A will tend to recoil along the x-axis.
Okay, sir.
Okay, so we have this j cap, right? And then we have B's momentum, which is purely along the x-axis. Okay. So by comparing this equation itself, you can see that if you look at the y component, you'll understand that E's y component of velocity has to be v naught sine alpha. Okay. So the x component on this side is ma v naught cos alpha. The y component on this side is ma v naught sine alpha. On the other side, the x component is mbvb minus A's x component of momentum, which I've written like this. And the y component is purely A's y component only, so they have to be equal, which is reflected in the impulse picture, because there is no impulse acting on A along the y axis, neither on B. So this generates our two equations. So MA V naught cos alpha is equal to MB VB minus MA VA X, and on the other hand, MA V naught sin alpha as expected is equal to MA into VA's Y component. So these are effectively our two momentum conservation component equations. Okay. So equation 2 gives you one value in itself. It gives you the value of VAY, which will be V naught sin alpha, which in this case will be 12 centimeters per second. But equation 1 gives you a relation between VB and VAX. And one more relation you will have to determine by using the coefficient of restitution. And solving those two equations will give you the two unknowns quantities, the value of VB and the value of A's X component of velocity.
So solved.
So how much are we getting? VBS?
So VB is 7 centimeters
Per second.
Yes, sir. So, yes, sir. And VAX is 2.34.
Have you taken coefficient of restitution as 0.8, beta?
Yes, sir.
Okay. Yeah, so the direction of VAX I have considered is correct?
Yes, sir.
Okay. Okay, so let me verify your. So can you tell me the equation you got for coefficient of restitution? Like, what is the separation velocity? Approach velocity we got here, right? What is the separation velocity?
So VA plus VAX plus VB is equal to
Yes,
EV
very good. Yes, very good. The separation velocity, which you can see in this diagram, the Y component has nothing to do with the separation velocity. It is the relative velocity along the x-axis, because the x-axis is center to center. So because they are going oppositely, it will become VB plus VAX, correct?
Yes, sir.
This is our separation velocity. Okay. And earlier we've seen this is our approach velocity. So this comparison of these two quantities will give us the second equation that we are looking for. In this case, I'll call it the third equation, but that is the coefficient of restitution equation. Dhruv, I'm just going through the doubt you have sent. UB is equal to VB I cap. Because why that is happening, let's understand. So this is very important. Okay. The direction of VB is along I cap because the collision impulse that acts on B because of A is along I cap. Okay. And initially, B was at rest. So an object which is at rest, you hit it with an impulse, its direction of momentum will have to be in the direction of the impulse. And the direction of that impulse is only I cap. Okay, so hope this is clear now, Dhruv.
So why do two colliding objects apply impulses on each other?
Oh, that is because the molecules cannot merge into each other. It has ultimately got to do with electromagnetic forces between molecules.
Then
If
so
two
they
liquid
deform
drops
each other?
collided with each other, then instead of applying impulse in this manner, they would probably merge into one liquid drop, right?
Yes, sir.
It has to do with material property after all. all contact forces, impact forces, all these things are to do with electromagnetism at the end of the day, because they are to do with how molecules, atoms, and fundamental particles of nature or physics interact with each other, but at the molecular level, not at the nuclear level, because then it would be nuclear forces.
Yes, sir. And sir, why do they apply forces on each other at all?
That has to do with the structure of matter, no, at the atomic level, and that is completely determined by the electrostatic forces between electrons and protons, and nucleus and electrons, those kind of things.
Then,
So,
sir, if I
for example, what you're asking is like a very basic question, that why a solid material has rigidity, no? Why it behaves like a rigid object, why its molecules cannot flow like the case of a fluid, right?
no, sir. So I'm saying if I walk into a wall, why will the wall apply force on me?
Same reason, no? Because the wall is a rigid body, no? And your head is also a rigid body, or your hand or whatever walks into it is a rigid body, no?
Yes, sir.
So it has to do with the nature of these two materials, no? Which are moving towards each other with some momentum, plus they are rigid. So they react to each other by applying reaction forces, no? That happens because they are rigid in nature. Whereas if you take two fluids in two containers and you push, they're flowing towards each other with momentum, they don't apply forces in the same kind of way. There will be some forces of interaction, but it will not be quite the same like two rigid bodies colliding, right?
Yes, sir.
So that again has to do with the nature of intermolecular interaction, no? How the molecules in a solid or rigid material are binded to each other through intermolecular forces, which are much stronger. So what intermolecular forces come from? They come from charge, actually, no? The charged particles of atoms.
Then, sir, when will we learn about this in depth?
Oh, to learn about this in depth, you have to learn material science. You have to become a specialist in material science. I mean, to a certain extent, you study states of matter in chemistry and you understand bonding and all this, no?
Yes, sir.
So so what you are talking about would be an extension of that into graduate level studies, right?
Okay, sir.
So that's part of a branch called material science. Okay. But for example, if you study chemistry also in more detail, molecular chemistry, etc., where you basically do like various different quantum mechanical models to understand molecular theory, and then you do some computer simulation also for molecular chemistry. So there again you'll see more aspects of this. So there's a lot of research that goes into it, that why materials have certain properties, where their elasticity comes from, where their ductility comes from, where their conductivity of both in terms of electrical conductivity and thermal conductivity, all these kind of properties, where they come from.
Okay, sir.
So that is again like fundamental science at very much a research level, right? Okay, so let's get back to it. So this equation 2 is showing us that directly my VAY is equal to V naught sine alpha, which when I work out is working out to 12 centimeters per second. So I've got one of the three unknowns, VAX, VAY, and VB. These are the three unknowns as of now. Okay, now from equation 1, now let me just write this in numerical form. So this side will be how much? 3 kgs multiplied by 9, right? Centimeters per second. And this will be 7 kgs into VB minus 3 into VAX. So what is this equation working out to be? 7 VB minus 3 VAX is equal to 27, where the unit of this equation on both sides is kilogram centimeter per second. It's a momentum equation, so it is in kg centimeter per second. It's non-SI unit. This is centimeters per second. Now, the second part of the, or you can say the third piece of the puzzle, is the coefficient of restitution. Okay, so also given to us that E is equal to 0.8, which means that separation velocity is 80% or 0.8 times approach velocity. So above we had written separation velocity as BB plus VAX, because VAX was actually in the negative I cap direction, and that is equal to 0.8 times V naught cos alpha, which we know is 9 from above. So we have one more equation now. So we have this VB plus VAX is equal to 0.8 into 9. That is 7.2. And this is in centimeters per second. Yes. Okay. So what we can do is we can multiply the below equation with 3 kgs, okay, and add the two. So if this was our equation 1, this was coming from our equation 2, and this we have written as our third equation. Okay, so this is our third equation. So equation 3 ko will multiply it with 3 kgs, okay, and add with equation 1. So we have 8 VB, right? Sorry, 7 plus 3, 10 VB, my mistake. We multiplied this with 3. Now. So adding this with equation 1, so 7 plus 3, 10 VB is becoming how much now? It is becoming 27 plus 3 times this. So that is how much? 21.6. Correct?
Yes, sir.
Okay, so what I'm getting VB as now, I'll get it as 4.86 centimeters per second. So from that, I will get VAX as 7.2 minus 4.86. So that will be how much now? 7.2 minus 4.86 will give us
2.34.
2 point. How much did you say? 34, no? Yeah.
Yes, sir.
Centimeters per second. Okay. So now I got this. So now in my vector form, I know what the final velocities are. VA is according to my system of axis, which is like that. It is minus 2.34 I cap plus 12 J cap in centimeters per second. Okay. And VB is 4.86 I cap in centimeters per second. Now I've also worked out earlier that alpha is 53 degrees. Now the only additional thing I need to maybe work out is beta. Suppose the question asks that. Okay. So that also we can work out by using vector algebra. I'll explain how. So beta, if you remember, is the angle between A's final velocity vector and A's initial velocity vector, because basically the idea is like this.
Sir,
Yes.
how did subtracting 2.34 from 7.2 give 4.8?
4.86 plus 2.34 is 7.2 only, no?
Yes, sir.
It's correct.
Yes.
The calculation is correct. Okay. Achha, so let's come back to this. So this is my V naught. Okay. This was before impact. Okay. And so this is the line of V naught. Okay. And now coming back to this. Okay. After impact now, my VA is over. Okay. Just a minute. Yeah. My VA is something like this, let's say. Okay. Won't be exactly perpendicular, but VA is, let's say, something like this. It's quite likely to be even an obtuse angle. I'm not sure. We'll see what it is. So in this diagram, this is my alpha, which I've already worked out as 53 degrees. That is alpha, but beta I need to work out. So beta, as you can see, it is the angle between the vector V naught and VA, where VA I have already written like this. And if you remember what was V naught was 9 I cap plus 12 J cap, no? In this component form.
Yes, sir.
Okay. So the angle between two vectors we can easily find out now. Beta will be cos inverse of the dot product of these two divided by the product of the magnitudes. I mean, here it will become a lengthy calculation because the final VO has a very strange magnitude and all. Okay, but in principle, it's something that you can calculate once you know its vector form. So for a question with better set values, it will be quite easy for you to numerically work out beta. Here we'll just leave it at this because VA's magnitude is going to take quite a bit of calculation. Square root of 144 plus 2.34 whole square. So I'm not going to sit and do that just now.
Excuse me, sir.
Yes, beta.
Sir, how are we supposed to solve questions like these in the exam?
You will be able to solve it. This is like through this example, I'll show you how we develop some standard method of solving.
Okay, sir.
Okay, just
But
like
isn't this process too long to be solved in an MCQ based type exam?
sorry, come again.
Sir, isn't this process too long? I mean, wouldn't the question take too
For
long
a single
for
MCQ
our
question,
standard
yes.
set?
For a single MCQ question, it is maybe long. But if this is part of a paragraph, okay, or if it is one of those digit answer questions, numerical questions like that, then and you might not be asked to solve the entire thing. No, you might just, for example, be asked to find B's final velocity.
Yes.
Okay, so we will develop some problem solving strategy also. You see, okay? For example, for one-dimensional collisions, now I think you will see that with all the solving methods that we've seen, it's quite fast enough to solve, no? With the formula and all that.
Yes, sir.
But yes, this is one of the more tricky parts of mechanics actually. Two-dimensional collisions or oblique collisions is one of the more tricky part of mechanics syllabus for 11th.
So done.
Just a moment. Right. So now let's see how actually this question can also be simplified. I mean, the way we solve the question can be simplified somewhat. Okay. So if you think about it, the way we solved it now, it is like two separate things which are happening. It's like a head-on collision which is happening along the x-axis, head-on inelastic collision, and along with that, you just superimpose the tangential velocity of A, which does not get affected by the collision. So you can, in your mind, you can break this up into two separate events. One is that tangential momentum that A is having, which does not get affected. And the other is that the head-on impact that happens along the x-axis. And you can solve it that way. So basically what I'm saying is that this initial velocity of A, which we had, okay, just before A comes in contact with B. Sorry, get this right here. So just before A comes in contact with B, okay, let's say I've broken this velocity into these two components already. So I've broken it into this ux and uy. And that was just the geometry you had to use to find out ux and uy, which was okay enough. That alpha was easy to understand geometrically. So this ux is the one which is creating like a head-on impact. So if you just saw the event of ux alone instead of uy also in the picture, then you can understand that it's a head-on collision between these two happening at a velocity of ux like this for A, okay, which we had worked out was how much now? That was 9 centimeters per second. Okay, coefficient of restitution was 0.8. Mass of A was 3 kg and mass of B was 7 kg. So after impact, if you just see this in isolation, after impact, B's velocity would be how much? It would be 1 plus E times MA, that formula, upon MA plus MB times that UX. So this would be 1 plus 0.8 into 3 divided by 3 plus 10 into this 9 centimeters per second. So 1.8 into 3 into 9 divided by 3 plus 7 in the denominator. So this is still a bit of a calculation, but when you work this out, this will come out to be whatever we had got earlier, 4 point something it was. But at the same time, so now what I'm saying is that after impact, B will have a velocity which is along this direction. That will be this, okay. Whereas A will have a velocity component which is along this direction. So this will now, with our formula, it will come with a negative sign. Okay, this will be MA minus E times MB divided by MA plus MB times UX. So it will be 3 minus 0.8 into 7. So 0.10 into 9. So this will be minus of 2.6 into 0.9. So 1.8 into 27. Yes, so this is giving us our 4.86, and this one giving us our, so this is VAX. Okay. And of course, what will happen is along with this, there will be this component of this, which will remain conserved. So, because there's no impulse that acts along that direction. So that will remain 12. Okay. So now that you've understood the concept of these type of collisions, you can see how you can simplify. It is like a superposition of a head-on impact along the x-axis, which is a line of impact. and tangential momentum. Which is unaffected by the collision. So it's just superimposed, it's added to this equation. Okay, but even with this simplification, it does involve more analysis and solving more number of things compared to head-on collisions or a simple application of work energy or a simple application of momentum conservation or things like that.
So the longer we ended up deriving all the formulae.
Sorry?
That we ended up deriving all the formulae with the
Exactly. So what we did now in the previous way we solved this, no, the two equations that we had written now for momentum conservation along the x-axis and for coefficient of restitution equal to separation velocity upon approach velocity, that process only was used for derivation of this formula. No?
Yes, sir.
So that's why I'm saying that once you know the process, if you remember the formula, it will always help you at the exam level, whether it is this kind of question or it is a more direct formula based question of head-on collision. It will always help you a little bit more. And it's not so easy, it's not so difficult to remember those formulae once you get used to the pattern. Okay? And you also remember the special cases and the logic of that formula and all that. You'll see all in all, it's pretty easy to keep them in mind.
Yes, sir.
But yes, this does require a bit of intensive work. Okay, paying attention to the derivations, maybe doing them a couple of times yourself as practice instead of directly jumping to the questions also. That will also help. And the thing is, there are lots of variations of questions. We will spend quite a bit of time after having gone through all these general cases and all, looking at a lot of variation problems also. So, but everywhere the fundamentals will remain the same, that any collision involving any number of bodies colliding, whether it is head-on, whether it is elastic, inelastic, oblique, whatever be the case, momentum conservation is always going to be the place in the case, unless of course it is colliding with a rigid surface which is fixed to the ground. Because in that we cannot write the momentum conservation equation, because the surface which is fixed to the ground, that is becoming part of Earth as a body. So that has infinite mass. So unless you want to try and apply momentum conservation to infinite mass, which will not give you any useful equation, it's not going to really work out. So in that, you just remember the concept of approach and separation velocity like we discussed. But collision of multiple bodies, none of them being rigidly attached to the Earth, will always involve conservation of momentum. In fact, next chapter, we will see that there's also something called conservation of angular momentum. So if rigid bodies or objects collide in such a way that they start spinning after the collision, like when a vehicle collides with the curve of the road or two vehicles collide, it's not just that they transfer linear momentum, but they also transfer angular momentum. So there's a second part to momentum conservation, conservation of angular momentum, which we'll see in that chapter, that is rotational mechanics. Okay. So if your fundamentals are clear from this chapter, again, you will find that easy enough to understand. Okay. So we are at a very critical and crucial juncture of mechanics for you people. Okay. In this chapter, you will see your entire knowledge of mechanics till date, whether that is work energy, the concept of impulse momentum, the concept of application of calculus, vector algebra, dynamics, everything is going to come together at one place, including the additional concepts of system of particles.
The projectile also.
Yes, I mean, you saw in the last lecture we discussed about how projectile motion can be incorporated into collisions.
Yes, sir. Sir, I've noted all this.
Okay, very good. So this is done. Okay, now next we are going to see something which is actually going to be for us like a theorem. But interestingly, in H.C. Verma, it's not given as a theorem in the theory part. Rather, he has given it as a question, as a derivation question in the exercise. So we will also do it as a derivation question. And then once we do that, we will remember this as a theorem. Okay. So now what we want to show is that if there is an oblique collision between identical masses like this, Okay. Identical masses such that one of them is at rest, one of them is moving, and the collision is perfectly elastic but oblique. So there is some collision parameter, impact parameter, sorry, it's not zero. So if we have this situation, so A and B are, let's say, identical in mass, and they collide obliquely in a perfectly elastic oblique collision. Okay. Then we have to prove that they will, after impact, the final velocities will be perpendicular to each other. So if mass of A is equal to mass of B, okay, and A collides obliquely in a perfectly elastic collision, with B, okay, which is initially stationary, as shown, then prove that their velocities after impact are perpendicular. Okay. So there are very interesting ways of proving this. Okay. And in fact, you can prove it by both interpretation of perfectly elastic. One way of interpreting perfectly elastic is that there is zero loss of kinetic energy. Another way of interpreting it is that it also implies that approach velocity is equal to separation velocity, or coefficient of restitution is unity. So we can go with either of these two interpretations of the meaning of perfectly elastic collision, but still we will come to the same conclusion that if we have identical masses and an oblique collision which is perfectly elastic, every time it does not matter what angle they collided, as long as it's not a head-on collision, they will separate perpendicular to each other. The paths after the impact are going to be along perpendicular lines.
It's approved.
So tell me the process, what you use for proving better.
Sir, what we did before only.
That method, you have taken the x-axis along the line of action and all that.
Yes, sir. And then I got VAX is equal to 0. So they're
Very
perpendicular.
good. Very good. Huh? Because they exchange momentum because their masses are equal. No? So along the x-axis, there will be exchange of momentum between A and B. So whatever that V naught cos alpha is, that will become the final velocity of B, and A's final velocity along the x-axis will become 0, whereas the y component will remain conserved. That is the method you used, Janvi?
Yes, sir.
Okay. Now try another method in the meantime. Okay, while I'm showing that method to everyone else, try the method of interpreting this, that there is zero loss of kinetic energy. See, that's also very interesting. And if anything, that's an even simpler way. Yes, Siddharth, that's correct. Okay. So even though here I have not given any indication of how much alpha is numerically, but we can see alpha is not 0 because there is an oblique collision happening. So we just assume some arbitrary value of alpha and solve the problem accordingly. So we can show that because the coefficient of restitution is 1, therefore A's final velocity will have to be purely along the x-axis, or that is, sorry, purely along the y-axis or in the tangential direction, whereas B's final velocity will be purely along the x-axis, which is the center to center line, which kind of proves that they are going to be perpendicular. So this is our center to center line. So I'll be taking this as the y-axis, which is our tangential axis. So you can also write this instead of x and y as normal and tangential axis. Okay. So the initial velocity vector of A initial velocity vector of A is like this. Let's say that is at some alpha. So V naught cos alpha is the approach velocity. It is the normal component. And V naught sin alpha is the tangential component. So now because we know that the collision impulse will act along this line, so we know that the tangential component remains conserved. So when we look at this thing, what is happening along the x-axis? So now we see that what is happening along the x-axis is there's a complete transfer of momentum which is happening. This is what will happen here. So these will be the final velocities. So VA after impact will remain V naught sin alpha j cap, and VB after impact will become V naught cos alpha I cap. So VA dot VB is 0. So this all is happening because of that, because E is equal to 1 and M1 is equal to M2. So that is my VB will become 0 times, sorry, it will become 1 into V naught cos alpha, and Vax will be 0 into V naught cos I, because we have that equation. Using that, so along the x-axis there is a simple, exchange of momentum that happens, and along the y-axis simply there is conservation of momentum for E. Okay, so as I said, having done the proof of this, we should remember this as a theorem now. Now, one more way of understanding the proof of this is an even simpler thing actually. There we don't need to even understand this line of impact and all that. We just need to apply the concept that kinetic energy is conserved in a perfectly elastic collision, and momentum is generally conserved in all collisions. So if this is our initial situation, and this is our final situation after impact, what we are trying to prove is that this angle should be 90 degrees. But keep in mind that the masses are equal. Okay. So momentum conservation will give us that mv naught is equal to mva plus mvb. So it's telling us that the vector sum of va and vb is equal to v naught because the masses are equal. And perfectly elastic. So I will interpret that as this is momentum conservation. So I will interpret perfectly elastic as conservation of kinetic energy. So half mv naught square is this. So once again, cancelling off this, we can see that va square plus vb square is equal to v naught square. Now, if you go back to a vector algebra, this is the condition for two vectors be perpendicular to each other. So magnitude of v naught is square root of va square plus vb square, and magnitude of v naught from the first equation is mod va plus vb. So mod va plus vb is root of va square plus vb square. And it can only mean one thing, that either one of the two is zero, which is not the case over here. The dot product is zero, so they are perpendicular vectors. Okay, but which of course also shows us that if the collision is not perfectly elastic for that reason, or let's say if the collision is elastic but at the same time the masses are not equal, then this condition will not be satisfied, because it's a special condition for this thing to happen, that both the masses should be equal, the collision should be perfectly elastic, and it should be oblique. It should not be head on.
So done.
Right. Okay. So, like I said, this is an important theorem to keep in mind. Okay. Now we can always get something which is somewhat simpler to understand than this kind of thing, because some information might be directly given to us in a problem. For example, we can get this type of question has appeared in JEE before also. We can get a question like this where a sphere comes and collides with a larger sphere, okay, but such that it is given to us that the first sphere after impact, it goes off perpendicular to the initial velocity. Okay. So given that MA is equal to 1 kg, MB is equal to, let's say, 4 kg, and after impact, A's velocity, so V naught is also given to us. Let's say it is 9 meters per second. So A's velocity is perpendicular, or you can say, another way of expressing this is A's velocity is of, or we'll say that after impact, A is deflected by 90 degrees. So V naught is 9 meters per second. After impact, A is deflected by 90 degrees, and its speed is suppose 3 meters per second. So find B's velocity after impact and also find the coefficient of restitution. So deflected by 90 degrees means it turns by 90 degrees. So its velocity's direction, because of the impulse of impact or the collision impulse, it turns by 90 degrees. So it goes off with the final velocity, which would be at 90 degrees with respect to the initial velocity. So this you can see is a simpler version of, numerically it is simpler to handle, okay? Because one angle is directly given to us, and that angle in fact happens to be 90 degrees. And also one final speed is given to us. So we just need two equations because two quantities are already known. Oh, you're getting E as such a large value, 2.045, is it? So that's not physically possible, right?
Yes, sir.
Okay. Let's do one thing. Let's change the question somewhat, okay? Because this is giving us a nonsensical result. So instead, what we'll do is we will keep the mass of B unknown. Okay? So we will say that we don't know what the mass is. We'll say MB is unknown, but instead coefficient of restitution is known. E is, let us say, 0.8. So now we'll ask ourselves that if this situation is giving us coefficient of restitution of 0.8, what does that mean about the mass of B? So that's another way we can do this question, okay? Because solving it right now is giving us a nonsensical answer, which means that two bodies like this colliding cannot have this result. E's velocity cannot become perpendicular. Okay? So anyway, if I go with this right now, this is the situation before impact. Okay? And after impact, what we are expecting is that A's velocity is something like this. And therefore B's velocity will be something like this. Okay? Because the momentum has to be conserved. And suppose this angle is some theta. Okay, so A's velocity initially was given to us as 9. And after impact, it is perpendicular. And it is how much? It is 3. Okay. So our momentum conservation equations will be such that MA into V naught is equal to MB VB cos theta, or if you take this as X and Y, write this as MB VB X, and 0 is MA VA minus MB VB sin theta, or MA VA minus MB VB y. So from equation 1, we'll get one component of B's velocity. From equation 2, we'll get another component of B's velocity. But that is provided we know the mass of B, which is given in this case as 4 kg. But then that is giving us an observed result for E, coefficient of restitution. So let me just check out how we can adjust the mass of B so that that will not happen. Perhaps we'll have to take them like more similar masses instead of 1 and 4. If you took it as 3 and 4, or maybe even 3.5 and 4, you would have got an acceptable value of coefficient of restitution. Or actually, I think make A heavier than B. Then, so one more thing we can do is, let's solve another case where we take MA as, let's try this. Let's take MA as 12 kg, MB as 4 kg, V0 as 9 meters per second, and VA as 3 meters per second, where VA is perpendicular to V0. Let's see if this works out.
So then tan alpha is 1 by 9.
Okay. This you are saying in which case, Vita? The first case?
The second one, this new values.
As a new values, okay. Yeah, so that's okay. No? Tan alpha can be 0.11 like that. Right? So alpha is a small angle. But anyway, let's solve the first part. Where now in the first part, what I'm doing is I'm taking MB unknown. Okay. So I have VBX as V0 upon MB. So it is 9 by MB. Okay, because I've taken MA as 1 kg. And I have B's Y component in the downward direction, of course, okay, as MAVA divided by MB. So that is 3 by MB. So these are the components of B's velocity that I'm getting. Now, what will be the coefficient of restitution formula over here? So you can see that this angle theta will be tan inverse of Y component divided by X component. So That will be tan inverse of 1 by 3. Okay. So now what will be my separation velocity? So in this diagram, you can understand that B's final velocity only, that is along the center to center line. Okay. So basically, if A is going off like this, and we have got this angle here as theta. So that means this angle is how much? It is 90 minus theta. So the separation velocity is going to be VB plus VA cos of 90 minus theta. So that will become VA sin theta. This is going to make so VB is 3 by MB square root of 10, isn't it? It's like this. So this is our separation velocity, and coefficient of restitution is 0.8. So our separation velocity has to be equal to 0.8 times our approach velocity. So we'll have to utilize this now. In the same diagram, what is our approach velocity? Our approach velocity would be V naught cos theta, and our separation velocity would be this thing, VV plus VA sin theta. Okay, so if tan theta is 1 by 3, then cos theta is 3 by root 10, and sin theta is 1 by root 10. So what was our VV? It was 3 upon MB root 10 plus VA, which was 3 sin theta, that is 1 by root 10. So this was 0.8 into V naught, which was 9, into cos theta, which is 3 by root 10. So this equation should now give us the value of MB. So this is the solution to the first part, where I have kept MB unknown. Instead of giving MB as 4 kg, I changed MB to unknown and gave you the value of coefficient of restitution. So this is the first part solution. And what I've done is I've kept this value, but this is unknown. So this won't be all that difficult to calculate also, because that root 10 into root 10 will work out. So it is 7.2 minus 1, that is 6.2 into 3 upon root 10 is equal to 3 by root 10 MB. Something like that.
Sir, MB is 10 by 6.2.
MB is 10 by 6.2, na?
Yes, sir.
Yeah, that's 100 by 62. That's about 1.61 kgs. Okay. Now, similarly, if I change the data to this one now, the second parts, just see what you will get. Take the mass of A as 12 kg, mass of B as 4 kg, and see what we'll get for coefficient of restitution. Now, in the second part, I'm asking you to calculate the coefficient of restitution instead of the mass of B. Okay, so in this case, you will see that the conservation equations will give us that MA V naught is equal to MB VB cos theta. So this will give us that VB cos theta or VBX is how much? It is 12 by 4, that is 3 times V naught. So 27 meters per second. And MAVA should be balanced by MBVB sine theta. So we get VB sine theta as how much now? Ratio of masses, that is 3 into VA. So this is 9 meters per second.
Sir, E is still unacceptable.
E is still unacceptable, is it? Okay, so let's check out. So theta is coming tan inverse 1 by 3 again. Okay. So what is our separation velocity going to be? It is going to be VB plus VA sine theta. Okay. So VB will be this time 9 root 10, right? And VA was 3.
Yes, sir.
Okay. And sine theta is 1 by root 10. So 3 by root 10. So this is our separation velocity, and our approach velocity
27 by
same as
root 10.
before. It's V naught cos theta is 27 by root 10. So our coefficient of restitution according to this should be 9 root 10 plus 3 by root 10 divided by 27 by root 10. Okay, so coefficient of restitution is coming out to be this time 93 upon root 10 divided by 27 by root 10. So again, it's unacceptable. Yes. So this is simply not working out. Sorry. I have to recheck what is happening in this case.
So it was about 2/3. Sorry.
Oh, actually, if you saw now that for an acceptable value of E, what is the condition that we got? That B is much lighter than A. Na? Oh no, it is almost double, 1.5 times, 1.62, like, whereas A was 1 kg. So maybe if we had taken MB as like if we had taken MA as 5 kg or 3.5 kg or something like that, we would have got some acceptable value of E. So again, this is not logically possible. Okay, two bodies of this kind of mass ratio 3:1, this collision cannot result in A getting deflected by 90 degrees. Yeah, actually, I thought as much. For A to get deflected by 90 degrees, it probably has to be lighter than B, but not so much lighter like we had taken before, that 1/4.
So what will, if it's very light, what will happen?
If it is getting deflected by 90 degrees, then its speed will be much closer, I think, to 9 meters per second than this. If A is very light, it is almost like B is an infinite mass compared to it. So if it hits at 45 degrees in an elastic collision, it will go off at 90 degrees.
Yes, sir.
Just imagine B's surface to be like a rigid wall. So there cannot be so much loss of kinetic energy for E in that case. So there are some kind of constraints involved over here of what kind of masses can have what kind of deflections and what kind of range of speeds they can have after impact and all that. So all this is actually very interesting. It's part of what we call classical mechanics of two rigid bodies or rigid body problems. Okay. But here we don't need to get into that much detail. Just we have to understand how to apply the momentum conservation and coefficient of restitution concept. Okay. So we will look at another interesting problem today. Okay, and this one is again not going to be something very difficult. So, yeah. So the next problem we'll see is our first example of a collision of more than two rigid bodies. Okay, namely, in fact, we are going to look at three rigid bodies colliding. Just a second. Okay, so suppose this is the top view of a system of spheres which is lying on a frictionless horizontal surface. Okay, so imagine gravity is going into the plane. Sorry. Yeah, so we are looking into a system of spheres from above. Gravity is going into the plane. Just a moment. We share that file. Yeah. Okay. So two of these spheres are in contact like this, and they are at rest. And the third sphere, which is also identical, is moving such that its velocity vector is exactly along the common tangent plane. So this third one is moving with a velocity. So that velocity vector is exactly along this, passing through the point of contact along the common tangent, or perpendicular to the center to center line. So it's like this sphere collides with both of these spheres simultaneously with an impact parameter equal to their radius. So this is the top view of a system of three identical spheres. Mass m and radius r for each. Okay. Three identical spheres A, B, and C on a smooth horizontal surface. So initially B and C are at rest and in contact. Okay. And A's velocity has a line of action along the common tangent at the point of contact. Of B and C. Okay, so the first part, what we'll do is, if A comes to rest just after impact, find the final velocities of A and B, sorry, of B and C, and also find the coefficient of restitution. I think we'll have just time for this part. The second part we can do for homework. If the coefficient of restitution is 1 for impact of A and B and of A and C. So there are two collisions happening simultaneously and both are having coefficient of restitution 1. Then find VA, VB, and VC after impact. Okay, so they are identical spheres of same mass and same radius.
So E
Yes.
is not given for part 1.
Sorry, come again. What is not given?
So what's E for part 1?
No, E for part 1 is not given, but instead it's given that A comes to rest. Okay, the sphere A comes to rest. Okay. So the hint to you is that there is some information that you're getting from geometry. As the three spheres come in contact, it's very easy to work out the center to center lines and therefore understand the angles along which the impulses act. Okay. And then there is momentum conservation, no?
Yes, sir.
So that will be sufficient actually, because you are given the information that A comes to rest. You will not be required to find out you will not require the coefficient of restitution. In fact, what will happen is once you find out B and C, so final velocity, You can also find out the coefficient of restitution in this case. And you'll see that in this case, E is less than 1. Okay, so can you people tell me what is the line of impact? What angle it's making with V0 for B and C?
60.
The collision impulse that acts on B and C, it will be at what angle?
So 60 degrees?
Yeah,
No, 30.
30 degrees with respect to V0, right?
Yes, sir.
So once you understand that, rest is simple. No? So you can see that B and C's final velocities will be at an angle of 30 degrees with respect to this V0, and E is coming to rest. Okay. Making a bit of a clumsy diagram here, but so this will have a velocity along the direction of impulse only. No? So this is VB. Now you'll also understand, because the angles are symmetrical, so the velocities are also symmetrical, which means that whatever coefficient of restitution A is having with respect to B, same it will have to have with respect to C also. So this angle is equal to this angle, because this is an equilateral triangle. So theta will be 30 degrees. It's bisecting that angle. So now you can see that MVB cos 30 plus MVC cos 30 will have to be equal to MV0, momentum conservation, because before impact, this is what was happening. We just had a V0 in this direction. Okay, and MVB sin 30 minus MVC, or by symmetry, you can just understand that the two magnitudes of VB and VC are equal. So from these two equations, you can see that. Okay. And from equation 1, you will see that VB is equal to VC, which will become V0 by root 3, correct?
Yes.
So these are the final velocities in magnitude, and their direction is at 30 degrees. Okay. Now, what about the coefficient of restitution? What you can say about that? So if you look at the impact between A and B, for example, before impact, A's velocity had what component towards B's center? Cos 30 component. So approach velocity is V0 okay. And now in this diagram, you can see that separation velocity for A and B is directly VB. So this is for A and B. So the coefficient of restitution is coming out to be, yes, very good, that's correct, 2 by 3. As I told you that you will get a value which is less than 1 in this case. So E is separation velocity upon approach velocity. So I'm applying it to this pair B and A and B, but you can apply it to A and C also, and it will be the same. So
Sir, but it's not just the collision of A with one sphere which is bringing it to rest, right?
it's
Okay.
the simultaneous impulse. Actually, what is happening now, that when they collide, there is one pair of impulses which acts like this. Okay. And another pair of impulses, let's say this is J1 and J1, and there's another pair of impulses which acts like this, J2 and J2. Now, symmetrically, they are the same because they are identical masses and both the coefficients of restitution are same. So the vector sum of these two is becoming along this direction for A.
Yes, sir.
And that is bringing it to rest. Okay, but nonetheless, there is some defined coefficient of restitution for each pair, because each pair of bodies, whether you look at A and C or A and B, they are approaching each other at a certain rate and then they are separating at a certain rate.
Sir, I have a doubt here only.
Hmm.
If there was no C, then would the coefficient of restitution stay the same?
But then A could not come to rest, you understanding better? Then it would be an oblique collision, A could not have come to rest in this situation, because see, the momentum of A is not directed towards the center of B. The only way A could have come to rest is if it had been a perfectly elastic head-on collision between A and B, because they are identical masses. You understanding the point, Vita?
Sir, a little bit.
See, remove C from the picture, but let A come and hit B in the same way. Is it possible for A to come to rest? No, no.
No, sir.
That's it, no? So this situation cannot occur then, no? Then that would be like the oblique collision which we studied before. So in spite of hitting B obliquely, how A is coming to rest? Because not only it's hitting B, it's also hitting C simultaneously, no? So the net impulse is acting in that backward direction, opposite to MB, not, and it's bringing it to rest.
So my doubt is that
Yeah.
the collision, which is A coming to rest, why are we attributing all of that to the E of each?
No, E is like a kinematical parameter, better. E is for a pair of bodies colliding. It is a comparison of their approach and separation velocity. You understanding, no? So as A is coming and hitting that point where it comes in contact with B and C, it is approaching B also and it's approaching C also, right?
Yes, sir.
And after the collision is over, B and C both start moving away from A. So each of them have some separation velocity, with respect to A.
Yes, sir.
So it's a kinematical parameter. It has nothing to do with anything else. It has to do with what is the rate of separation with respect to the rate of approach.
Yes, sir. I got it.
So that works out to be 2/3 for both the collisions happening here, because everything is symmetric. Okay. So people, I'm a bit stretched for time today here. I have some appointments, so I'll just conclude this. The second part you work out yourself. Okay. After going through this, okay. In the second part, I've changed it. The A's final velocity is not given. Instead, the collision is perfectly elastic. So try and figure out what will be the final velocities of A, B, and C. Okay. I'll send you the notes and recording of both these lectures this week. And please work on the questions from your module now. Try to finish up everything for center of mass. Other than variable mass system, you should be able to solve everything. We will start discussing the questions in the next week's lectures also. Okay.
Sir, in the module, the answers are not given in the back.
Answers for this module are not given, is it?
Yes, sir.
Yeah, so for system of particles, it's not given.
Okay, I will look into that. I will get that sent. Okay, people, that's it for today.